Imagine a world where secrets could stay truly secret. A world where spies couldn't steal sensitive information, no matter how hard they tried. This is the promise of quantum key distribution, or QKD. In our world today, we use codes to protect our secrets, but these codes can be broken. A clever eavesdropper could intercept our messages and steal our secrets. QKD changes the game. It uses the laws of quantum mechanics to create unbreakable codes. With QKD, we can finally build communication networks that are truly secure. This new technology is like something out of science fiction, but it's real, and it's changing the way we think about security. Let's take a journey into the quantum world to understand how it works. To understand QKD, we need to take a trip into the quantum realm. This is the world of atoms and photons, where the familiar rules of physics no longer apply. In the quantum world, things aren't so clear-cut. Particles can be in multiple states at once. It's like a coin spinning in the air, both heads and tails at the same time. This mind-bending concept is called superposition. Imagine trying to measure this spinning coin. The act of observing forces the coin to choose a side, heads or tails. The same thing happens in the quantum world. When we try to measure a particle in superposition, it collapses into a single state. The quantum world is full of surprises. It's a strange and wonderful place that challenges our understanding of reality. Let's dive deeper into the strange principles that make QKD possible. We've already met superposition, where particles exist in multiple states simultaneously. But there's more. Heisenberg's uncertainty principle tells us that we can't know both the position and momentum of a particle with perfect accuracy. It's like trying to nail down a jelly. The harder you push on one side, the more the other side slips away. Then there's the no cloning theorem. This fundamental principle states that it's impossible to create an exact copy of an unknown quantum state. It's like trying to photocopy a dream. You can try, but you'll never capture the original perfectly. These three principles, superposition, uncertainty, and no cloning, are the cornerstones of quantum mechanics. They might seem bizarre, but they hold the key to unbreakable encryption. So how do these mind-bending quantum phenomena translate into secure communication? Let's break down the process of QKD. Imagine two people, Alice and Bob, who want to share a secret message. They need a secure way to generate a shared key, which they can then use to encrypt and decrypt their communication. Alice starts by sending photons, tiny particles of light, to Bob. These photons are prepared in specific quantum states, representing bits of information. Bob receives the photons and measures their properties, like their polarization. Because of the uncertainty principle, even Bob doesn't know the exact state of each photon until he measures it. Section 5. Catching a quantum eavesdropper. What if an eavesdropper, Eve, tries to listen in? Here's where the magic of quantum mechanics kicks in. Observing a quantum system changes it. If Eve tries to intercept and measure the photons, she'll inevitably leave traces. She can't measure the photons without disrupting their delicate quantum states. Alice and Bob have a clever way to detect Eve's meddling. After sending and receiving the photons, they publicly compare notes about a portion of their measurements. If their measurements don't match, they know someone tampered with the photons. Eve's eavesdropping attempt is revealed, and they discard the compromised key. Section 6. Quantum keys come in different flavors. There's more than one way to skin a cat, and there's more than one way to implement quantum key distribution. Over the years, scientists have developed different protocols, each with its own strengths and weaknesses. One of the earliest and most famous protocols is BB84. It uses the polarization of photons to encode information. Another popular protocol is E91, which relies on a phenomenon called quantum entanglement. Then, there's QKD, which stands for Continuous Variable Quantum Key Distribution. This approach uses continuous properties of light, like its amplitude and phase, to carry information. Each protocol has its own quirks and advantages. Some are more resistant to noise, while others offer higher key rates. The choice of protocol depends on the specific application and the desired level of security. Section 7. The promise and perils of quantum security. Quantum key distribution offers a tantalizing glimpse into a future where communication is truly secure. But like any emerging technology, it comes with its own set of challenges. One of the biggest hurdles is distance. Photons are fragile creatures, and they tend to get lost or absorbed as they travel through optical fibers or the atmosphere. This limits the range of current quantum key distribution systems. Another challenge is the cost. Building and deploying quantum key distribution systems can be expensive, especially for long-distance communication. This makes it difficult to compete with traditional encryption methods, at least for now. Despite these challenges, quantum key distribution is rapidly evolving. Scientists and engineers are constantly pushing the boundaries of what's possible, developing new technologies and techniques to overcome these limitations. Section 8. Quantum security in action. While quantum key distribution might sound like science fiction, it's already being used to secure sensitive communication in various sectors. Governments and militaries are early adopters of quantum key distribution, using it to protect classified information from prying eyes. Financial institutions are also exploring quantum key distribution to secure transactions and prevent financial fraud. Healthcare providers are interested in using quantum key distribution to safeguard patient data and ensure privacy. And telecommunication companies are investigating quantum key distribution as a way to build more secure networks for the future. As the technology matures and becomes more affordable, we can expect to see quantum key distribution being adopted in even more areas of our lives. Section 9. A future secured by quantum laws. The future of secure communication is quantum. Quantum key distribution has the potential to revolutionize the way we protect our information, ushering in an era of unbreakable encryption. Imagine a world where online banking is completely secure, where medical records are truly private, and where governments can communicate without fear of espionage. This is the future that quantum key distribution promises. Of course, quantum key distribution is not a silver bullet. It's not a magical solution that will instantly solve all our security problems. But it's a powerful tool that, when combined with other security measures, can significantly enhance our defenses against cyber attacks. As we continue to explore the weird and wonderful world of quantum mechanics, we can expect to see even more exciting advances in quantum cryptography. The future of security is bright, and it's powered by the fundamental laws of the universe